Hey everyone, so hopefully you're enjoying your first day of e-learning. Today I'm going to do solar power calculations, and you can work ahead and do this today, or it's due I think on the third day. So technically it's not due until next week, but if you'd like to get a head start, the first thing that I need to correct though, it says 1 milliwatt hour is equal to 1 kilowatt hour. That's actually wrong. It's supposed to be 1,000 kilowatt hours. Alright, so it says a grid-connected residential PV system, PV stands for photovoltaic, is installed on a roof. The PV system has an area equal to 50 square meters and the initial cost is $50,000. Alright, so it says the operating system is in a location where it gets this many kilowatt hours per meter squared per day. Calculate the average amount of solar energy incident on the photovoltaic array each day. Alright, so the first thing you want to do is this would actually look like this. 5.0 kilowatt hours per meter squared per day. Alright, and all you have to do is just multiply the 5.0 kilowatt hours per meter squared per day times how many square meters it is. And it tells you up here it's 50. So times 50 meters squared. Alright, and then if you want to, you can get out your calculator. So I'm going to get out my nice handy dandy calculator. 5.0 times 50. Wow, 250. Alright, so if you notice, the meter squared from the bottom here will cancel out with the meter squared up here. So now it's 250 kilowatt hours per day. Alright, so that's the average amount of solar energy, or PV, each day. Alright, it says the next one, the efficiency of the PV system equals 10%. That is, 10% of the solar energy is transferred into useful electric power. Calculate the daily average electric energy produced by this system. Alright, so what you're going to do is you're going to take the answer that you got in A and just multiply it by 10% as a decimal, which is just 0.1. Alright, so if it's 250 kilowatt hours per day, and it's only 10% efficient, 10, you divide it by 100 to get it as a decimal, that would be 0.1. 250 times 0.1, if you don't know how to do this in your brain or you want to check yourself, 250 times 0.1, it's 25. Alright, so it's 25 kilowatt hours per day, which is not a lot of kilowatt hours at all. So remember, the Three Gorges Dam in China can produce I think it's like 22,000 or 225,000 kilowatt hours per day. Or it might even be megawatts. It's ridiculous. Alright, calculate the average amount of energy, electric energy produced by this system each year. So if this is 25 kilowatt hours per day, we just need to convert this into a year. So we're going to do 25 kilowatt hours per day. Alright, we're going to multiply it, and I'm going to do the whole factor label thing so that I can just show you how the units would cancel out. So you would put day up here because you want the day to cancel out with this day up here. And then you would put year on the bottom. Alright, how many days are in 1 year? There's 365. Technically there's 365.25, and then you add up the 0.25s, and that's how you get a leap day, but that's neither here nor there. Alright, so now on my calculator I'm going to do 25 times 365, and that equals 9,125 kilowatt hours per year. Alright, over the next 20 years, U.S. annual electric energy consumption is projected to increase by 1.5 trillion kilowatt hours per year. How many rooftop PV systems would be needed to supply 10% of this additional energy? Round your answer to the nearest million. Alright, so the first thing that I want to do is I'm going to write this 1.5 trillion kilowatt hours per year in scientific notation. So if you didn't know this already, 1.5 trillion is 1.5 times 10 to the 12th, and it's kilowatt hours per year. Okay? So it says how many rooftop PV systems will be needed to supply 10% of this energy. So I'm going to take this number and I'm going to multiply it by 0.1, because that would be 10%. Alright, and if you remember how to do scientific notation and all that stuff, You could do it with this one, or this year they're going to let you use a calculator on the AP exam. So 1.5 second E12 times 0.10. Alright, it's 1.5 times 10 to the 11th. So 1.5 times 10 to the 11th, and that's going to be kilowatt hours per year. Alright, now it says how many rooftop PV systems would need to be needed. Round your answer to the nearest million. Alright, so now what you're going to do is you're just going to take this number, the 1.5 times 10 to the 11th kilowatt hours per year, and divide it by the answer that you got in C. So I'm just going to divide this by 9,125. So I'm going to do it on my calculator. 1.5 second e to the 11 divided by 9,125. And here's the answer that I got. You can put it in scientific notation mode on your calculator if you want. So here's the answer I got. 1.64 times 10 to the 7th, or if you want to write it out as a normal number, it can be 16438,356, comma, so it's basically about 16 million. Alright, so 16 million of these things. Alright, so now it says calculate the cost of installing these residential PV systems. So I rounded my answer to the nearest million. Alright, so I'm going to do 16 million times, and up here at the top it tells you the installed cost of this system is $50,000 per each one of these things. So I'm going to multiply this by $50,000. Alright, so if you want to, we can turn 16 million into scientific notation, or you can just write it as a normal number if you wanted to. So 16 million times 50,000 is going to be equal to, so 16, 1, 2, 3, 4, 5, 6, times 50, 1, 2, 3. Alright, this says 8 times 10 to the 11th dollars. Alright, or 8 and then basically 11 zeros after it. Alright, so you can just leave it in scientific notation there. Alright, assuming that the electric energy produced by these PV systems is worth 10 cents per kilowatt hour, these residential systems would generate electric energy worth $15 billion per year. Calculate the simple payback for these PV systems. Alright, so what they want you to do is they want you to calculate how many years it's going to take for them to pay back this amount. Alright, so what you're going to do is you're going to take the number that you got in E and just divide it by this 15 billion. Alright, so this is 8 times 10 to the 11th dollars per year. We're going to divide it by 15 billion, which is times 10 to the 9th. Alright, now I'm going to do it on my calculator. Alright, and the answer that I have here says that it's going to take them about 53 years. Technically it's 53.333 years. But it says round to the, the nearest number of years. So it's going to take them about 53 years to pay this back. Okay? So, now let's move on to the next one, which I'm kind of annoyed because I don't understand why I put this down here and then I'm going to have to use it on the next one. So a 30 meter squared roof is 80% covered with an array of photovoltaic cells. Flipping on to my next page. It says, if the roof receives 6 kilowatt hours per meter squared per day of solar energy, calculate how much the array is receiving each day. Alright, so the first thing that you probably want to do is you probably want to take the 30 meters squared and multiply it by 0.80. And why am I doing that? It's because it says it's 80% covered with an array of photovoltaic cells. So the 30 meters squared is not fully covered by all these. So 30 times 0.8, that'll get you 24 meters squared of the roof is covered with these photovoltaic cells or solar panels. Alright, so now what you're going to do is you're going to do 6 kilowatt hours per meter squared per day, and you're going to multiply it by the 24 meters squared, and the meters squared will cancel each other out. So 6 times 24, that's 144, and that's going to give you kilowatt hours per day. Alright, so again what I did was I took the 30 meters squared from the previous thing, multiplied it by 0.8 because only 80% of the roof is covered with solar panels. And that gives me 24 meters squared of solar panels. Then the roof receives this many kilowatt hours per meter squared per day. So I took the 6 kilowatt hours per meter squared per day, multiplied it by the 24 meters squared, and I got that it's going to produce 144 kilowatt hours per day of electricity. Alright, so letter B, it says, if this array is only 40% efficient at converting solar energy to electrical energy, how much does it actually produce? And round it to the nearest whole number. Alright, so what this is saying is it's saying that 144 kilowatt hours per day, that is if it is 100% efficient, which it is not. It's only 40% efficient. So I'm going to multiply this times 0.40. 124 times 0.4, that gives me 57.6 kilowatt hours per day. And the question says round to the nearest whole number. So I'm going to round this to 58 kilowatt hours per day. So rounded, the little numbers, the little squiggly lines means approximately. Alright, if a town consumes 100 megawatt hours of energy in one day, how many arrays would the town need to install on individuals' houses? Assume all houses are the same size and round to the nearest whole number. Alright, so the first thing that I see is that the town uses this many megawatt hours in one day. And the array can produce this many kilowatt hours per day. So let's take this 100 megawatt hours, and this is per day, and we're going to convert the megawatt hours into kilowatt hours. So to get the megawatt hours to cancel out, I'm going to put it on the bottom here. So megawatt hours goes here, and then kilowatt hours goes here. Alright, and from the previous sheet where I goofed, 1 megawatt hour is 1,000 kilowatt hours. So I'm going to put that in for my conversion factor here. So this is going to be 1,000, and this is going to be 1. Alright, so that converts it into kilowatt hours. Alright, now you're going to multiply that, well, that should be an X. You're going to multiply this times kilowatt hours per day that the photovoltaic system can produce. So in one day, it can produce 58 kilowatt hours. Alright, so let me get my handy dandy calculator out. And I'm going to do 100 times 1,000 divided by 58. Alright, and the answer is 1,724.14. That's how many arrays they would need. So I'm going to put arrays there, which is the same thing as PV cells. Alright, so I'm going to round it to approximately 1,724 arrays. Okay? So that's the answer there. Alright, if each array system costs $35,000 to construct and install, what would the total cost be? Alright, so I'm going to take the 1,724 arrays, and I'm going to multiply it by $35,000 per array. Okay, so 1,724 times 35,000, and I'm going to put it in both scientific notation and normal. Alright, so 6034, 1, 2, 3, 4, so 1, 2, 3. So it looks like it's going to cost about $60 million to convert this town. The answer in scientific notation is 6.034 times 10 to the 7th. Okay, and this is in dollars. Alright, so that's kind of a lot of money, but I mean, if you want to convert to PV, it's probably going to be pretty expensive anyways. Alright, letter E. Assume each house can sell excess power back to the electrical company for 10 cents per kilowatt hours. Each house uses 28 kilowatt hours per day in electricity. How long in years will it take for a homeowner to recover their $35,000 investment? This is referred to as the payback period. So what I'm going to do here is each house uses 28 kilowatt hours here. And if you remember up here somewhere, it tells you that each house uses, let's see, it said something about 58. Yeah, there it is. Alright, so each house can produce 58 kilowatt hours per day, but they only use 28 kilowatt hours per day. So if they can kilowatt hours per day minus 28 kilowatt hours per day, that's going to give me 30 kilowatt hours per day that they can sell back to the electrical company. Alright, so if they have 30 kilowatt hours per day, let's see how many dollars they can save per day. So kilowatt hours goes here, and then dollars is going to go here. Alright, and up here for 1 kilowatt hour, the going rate is 10 cents or $0.1. Alright, so if you want to do this on the calculator, you can. 30 times 0.1 is just going to be $3 per 1 day. Okay? So now we're going to need to convert this into how many dollars they can save per year. So I'm going to put days here, and then 1 year is here. There's 365 days in 1 year, so 3 times 365 is going to be 1,095 dollars per year. Alright, so now what you want to do is you want to take the $35,000 that they spent at the very beginning to pay for this entire system and divide it by the amount of money they save per year to get how many years it's going to take them to pay this back. Alright, so we're going to do $35,000, that's how much they paid originally, divided by 1,095, that's how much they save per year by selling this electricity back to the power company. We're going to do 35,000 divided by 1,095, and that's going to give us 31.96 years, which is approximately 32 years. So there's your final answer for that. Alright, hopefully you found this helpful. If you have any questions, let me know.